one of the greatest mysteries of science. Did anything exist before the universe? The Big Bang Theory states that our universe originated about 13.8 billion years ago, expanding from an unimaginably hot, dense state into the vast cosmos we see today. This beginning was marked by a rapid expanse of space cooling and the formation of the first particles and atoms. But the before moment, the time previous to this cosmic birth, remains shrouded in uncertainty. It's possible that time and space were born together with the Big Bang, a point beyond which our current laws of physics cannot peer. Yet, human curiosity compels us to keep asking the question. Scientists and philosophers have long pondered whether the Big Bang was truly the beginning or just one chapter in a much broader cosmic story. In today's documentary journey, we'll explore what modern science can tell us about the origin of time, examine new discoveries that expand our understanding of the early universe, and consider bold theories that go beyond the Big Bang itself. Let's start with the fact that, according to our best scientific understanding, the Big Bang marks time zero, the beginning of the universe as we know it. In a single instant, all space, time, energy, and matter emerged from an initial singularity, a point of infinite density. In the first fraction of a second, the universe underwent rapid inflation, expanding faster than the speed of light in a space that was itself expanding. This set the stage for everything to come. 1 second after the Big Bang, the universe was a hot, opaque soup of particles. Within minutes, the first light chemical elements formed in a process called primordial nucleosynthesis. The early cosmos was extremely hot and dense, so hot that atoms couldn't yet hold together. Light, or photons, were constantly scattered by free electrons, meaning it couldn't travel far. For the first few 100,000 years, the universe was essentially foggy and opaque. As expansion continued, the cosmos cooled, and fast forward 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with nuclei to form neutral atoms. This moment, the epoch of recombination, changed everything. Now that electrons were bound in atoms, light could travel freely through space for the first time. The original fog lifted, and light burst across the cosmos. This ancient light still surrounds us today, in the form of a faint glow from all directions. Stretched over billions of years of cosmic expansion into the microwave range, we call it the cosmic microwave background, or CMB, and it's literally a picture of the universe in its infancy. By observing the CMB, scientists can see what the universe looked like when it was only 380,000 years old, practically a newborn compared to its 13.8 billion year lifetime. This is the oldest light we can observe, a relic image of the fireball of the Big Bang itself. Discovered in the 1960s, the cosmic microwave background has been measured in increasing detail over the decades using satellites and telescopes. It carries a wealth of information. The speckled pattern of tiny temperature differences across the sky is not random. It encodes the seeds of the cosmic web that formed later. Regions that were slightly denser on this early map eventually collapsed under gravity to form galaxies and clusters. In fact, the CMB is a blueprint for future structure, showing the hills and valleys in the distribution of the original matter. It also gives insights into the composition and shape of the universe. Decades of analysis have shown that ordinary matter, the stuff that makes up stars, planets, and us, accounts for only about 5% of the total content of the cosmos. The rest is dark and mysterious. About 27% is dark matter, and roughly 68% is dark energy, according to measurements of the CMB's properties. Remarkably, new observations continue to refine this picture. In March of 2025, researchers from the Atacama Cosmology Telescope, or ACT, and Princeton University released the most detailed images of the CMB to date, the clearest infant pictures of our universe yet, with 5 times the resolution of the previous full sky map made by the Planck satellite. ACT's extensive survey data even captured the polarization of this ancient light. This polarization, this directional orientation of CMB light waves, reveals how much matter moved in different regions of the young universe. Before, we got to see where things were, and now we also see how they're moving, explains Dr. Suzanne Staggs, director of ACT. These high-resolution images show subtle changes in the density and velocity of the primordial gas, the fine details of those early hills and valleys. This kind of data helps scientists answer long-standing questions about how our cosmos evolved from simplicity into complexity. And it's astounding. By measuring light that's traveled over 13 billion years, we can see the universe as it was just a few hours after its birth on a cosmic scale. If the CMB represents the thermal radiation of the infant universe, what happened next in cosmic history? After recombination, the universe entered the Dark Ages, literally. When the fog had cleared, the background glow gradually faded, and no new light had yet appeared because stars had not yet formed. This era ended when the first generation of stars ignited, likely around 100 to 200 million years after the Big Bang. These earliest stars, often referred to as population 3 stars, were probably massive, short-lived beacons that began to illuminate the young cosmos. They gathered in protogalactic clouds, marking the beginning of galaxy formation. For example, MOMZ-14 galaxy, based on observations, was undergoing a rapid star formation phase. At the time of its discovery, and its chemical composition, rich in nitrogen in relation to carbon, resembles the makeup of ancient globular star clusters in our Milky Way. This suggests that even in this very early epoch, star formation may have occurred differently than in later periods. These discoveries force astronomers to revisit their assumptions about how quickly small initial fluctuations seen in the cosmic microwave background could condense into fully formed galaxies. How could such massive, bright galaxies form so quickly? Were stars and galaxies forming more efficiently than our models predict? Or is our understanding of cosmic chronology? As new observatories come online, we expect to peer even closer to the Big Bang, possibly observing objects from the era of the very first stars. However, no matter how powerful our telescopes become, they will never be able to see what happened before the Big Bang. For that, we must turn to theory. Over billions of years, under the influence of gravity, matter in the universe gathered into a vast cosmic web. Galaxies are not evenly distributed. They form filaments and sheets, with large voids between them. This web-like pattern can be traced back to the initial fluctuations seen in the cosmic microwave background. Generally, our cosmological models, based on the Big Bang theory and an expanding universe filled with dark matter, predict that there is an upper limit to the size of large structures. The cosmological principle is a cornerstone of modern cosmology. It states that on very large scales, the universe should be roughly homogeneous, without enormous clusters or distinct patterns dominating one region over another. Essentially, when averaged over hundreds of millions of light years, every part of the universe should look more or less the same. According to standard theory, the largest coherent structures that can form should be around 1 billion light years across. That's why astronomers were surprised to find structures that far exceeded those dimensions. In 2024, researchers discovered a massive ring-shaped pattern of galaxies and galaxy clusters they dubbed the Big Ring. It spans about 1.3 billion light-years in diameter and roughly 4 billion light-years in circumference. We observed this structure as it was around 9.2 billion years ago. Essentially, that's how long its light took to reach us. Intriguingly, it lies near another colossal structure, known as the Giant Arc, which itself stretches an astounding 3.3 billion light-years. To put these scales in perspective, the Milky Way's own supercluster is only about 0.5 billion light-years in diameter. The Big Ring and the Giant Arc are truly leviathans on the cosmic stage. Moreover, a detailed analysis suggests that the Big Ring isn't really a ring. It may actually be a spiral or corkscrew shape twisting through space. If we could see it with the naked eye, which we obviously cannot due to its distance and faintness, one researcher said it would appear about 15 times wider than the full moon in our sky. This feature defies explanation using our best theories about the universe. The Big Ring is too large and too structured to be easily explained by the usual mechanism of baryon acoustic oscillations. Those pressure waves in the early universe could lead to a large-scale galaxy distribution, but they should appear as roughly spherical shells, not elongated rings, and not on this massive of a scale. If the data holds up, it could mean that our assumption about large-scale homogeneity might need revision. Neither of these two ultra-large structures is easy to explain in our current understanding of the universe, says Alexia Lopez, the scientist who discovered them. Their enormous sizes and unusual shapes must surely be telling us something important. But what exactly? One possibility is that such superstructures are statistical flukes, random clumps that, by coincidence, turned out to be larger than expected. But the likelihood of discovering not just one, but several gigantic structures, others include the Sloan Great Wall, the South Pole Wall, and the massive quasar groups, becomes increasingly small. Another intriguing idea is that they hint at new physics or new aspects of the universe's initial conditions. Perhaps some exotic process in the early universe gave rise to these megastructures, going beyond standard inflationary cosmology. For example, cosmic strings, hypothetical ultra-thin defects in space-time left over after the Big Bang, could, if they existed, have influenced the distribution of matter on enormous scales. These are speculative objects, but they represent the kind of new physics scientists invoke to explain such anomalies. A different idea proposed by the renowned physicist Sir Roger Penrose is even more radical. He suggests that these structures might be signs of a universe that existed before the Big Bang. In Penrose's conformal cyclic cosmology, our Big Bang was not a beginning, but rather a transition between cosmic aeons. If true, then traces of the previous universe could appear in our own universe. Penrose even suggested that ring-like imprints in the cosmic microwave background could be evidence of gravitational waves from the collapse of an earlier universe. Although most cosmologists are skeptical of such claims, the very existence of such objects forces us to consider that we may not fully understand the physics of the early universe. Let's summarize what we know so far. The Big Bang marks the starting point of the universe's expansion, and for the first few billion years, this expansion slowed due to gravity. But in 1998, researchers made a shocking discovery. The expansion was actually accelerating. Something unknown, later named as dark energy, was pushing the cosmos outward, overcoming gravity on large scales. To this day, dark energy remains one of the deepest mysteries in cosmology. We know it makes up about 68% of the universe's contents, and acts as a kind of anti-gravity, driving galaxies apart. For decades, the simplest assumption has been that dark energy is a cosmological constant, an unchanging property of space itself, possibly linked to vacuum energy. In our best model, the so-called lambda CDM model, where lambda stands for the dark energy, this force remains constant over time, leading to the universe accelerating exponentially forever. However, very recent data suggests that this may not be the whole story. Data from the Dark Energy Spectroscopic Instrument, or DESI, which has surveyed millions of galaxies and quasars, indicates that dark energy's influence may be evolving over cosmic time. In early 2025, scientists analyzing 3 years of DESI observations reported new evidence that dark energy has weakened over billions of years. In other words, rather than delivering a constant push, dark energy's repulsive effect may be gradually decreasing. The DESI results tantalizingly hint at an evolving dark energy, says Dr. Arjand of NSF's Noir Lab. If it's true, this would dramatically shift the picture. It could mean that the universe's acceleration won't continue indefinitely. In fact, as one researcher noted, whatever is causing the universal expansion may be decaying or decreasing in strength. This raises major questions about the fate of the universe. Will acceleration eventually slow or even stop? Could gravity ultimately regain control, leading to a slowdown in expansion or even a future collapse? We don't know yet, but it's clear that the once established idea of constant dark energy is now under scrutiny. Just like the nature of dark energy, another invisible foundational component of the universe is under close investigation: dark matter. Dark matter, invisible except through its gravity, is believed to form the scaffolding for galaxies and clusters. It plays a critical role in our simulations of structure formation. Without it, we can't easily explain how galaxies formed so quickly in the early universe. However, despite decades of searching, dark matter particles have never been directly detected and their true nature remains unknown. This has led some scientists to explore bold alternatives to the standard Big Bang model that would eliminate the need for both dark matter and dark energy entirely. This bold proposal came from Dr. Richard Liu, a physics professor who in 2025 put forward a new model of the universe that questions the very idea of a single Big Bang. According to Liu, the universe's expansion and the formation of cosmic structures could be explained not by one event, but by multiple mini-bangs or transient singularities that occurred sequentially. Instead of a single initial explosion followed by a continuous acceleration driven by dark energy, Liu suggests that stages that manifest as bursts of energy and matter entering the universe at different times might explain what we observe, effectively replacing both dark matter and dark energy with those sudden acts of creation. During each of these bursts, matter and energy flood the cosmos uniformly everywhere at once, and then the singularity winks out. These bursts occur so rarely and rapidly that we wouldn't observe them directly. They resemble cosmic flickers that leave behind shifts in the rate of expansion and give rise to new structures. Between the bursts, the universe coasts along with no need for any mysterious dark energy permeating space. The idea is striking, because it effectively revives aspects of the old steady-state hypothesis, which proposed the continuous creation of matter, but in a way that doesn't violate conservation laws. Liu points out that, unlike the classical steady-state model, which was deemed impossible because it required continuous creation of matter from nothing, thus violating energy conservation, his transitional singularities appear and vanish so quickly that they circumvent such violations. For an infinitely brief moment, a burst adds mass energy everywhere and then disappears. Interestingly, this can be formulated in a way that doesn't violate physics as we know it. Though it certainly stretches it, the effect of these temporary singularities would also create a kind of negative pressure within the structure of the universe, much like dark energy does. In essence, each burst could trigger a period of accelerated expansion, solving the dark energy puzzle for that era, and also seeding fluctuations that lead to galaxy formation, addressing the role of dark matter. According to the paper, the Big Bang itself might have been just the first in a series of such bursts, the one that started it all, followed by others. In the standard model, there was only one singular creation event. In Liu's model, there are many. This is a radical departure from conventional thinking, and naturally at this stage, it remains speculative. But quantum physics pushes those boundaries. Some models of quantum gravity, such as loop quantum cosmology, propose that the Big Bang could have been a big bounce, where a previous universe collapsed and then rebounded into ours. In these models, time continues through the bounce. So there was a before, namely the pre-bounce universe of which we might even find traces in our current cosmos. It's a compelling idea that perhaps the Big Bang was a transition, not a creation from nothing. If dark energy really is changing and might eventually reverse as DESI results suggest, we can imagine our universe one day contracting, ending in a big crunch, which could spark a new explosion. Of course, this is only speculation, but it shows that the boundary between before and after the Big Bang is a topic of active and serious research. The evidence we have today paints a picture of a universe that's surprisingly well described by the Big Bang theory, yet, at the same time, full of surprises that challenge it. As for now, the question what was before the Big Bang remains unanswered. It lies at the very frontier of scientific understanding, where empirical data is scarce and imagination collides with rigorous mathematics. Yet, as we've seen, science is making remarkable strides in illuminating the earliest chapters of cosmic history. Will we ever find direct evidence of a reality before the Big Bang? Perhaps not directly, but indirect clues may emerge. If our universe is just one of many cycles, then maybe future observations of the cosmic microwave background or galaxy distributions will reveal subtle patterns left behind by a previous cosmic cycle. If the Big Bang was one in a series of bursts, then we might find fossil imprints of those fleeting events in the data. Or perhaps one day, a new unified theory of quantum gravity will allow us to deduce the state of existence that gave rise to our universe. Which scenario do you find most plausible? The void hypothesis doesn't just challenge our understanding of cosmic structure and expansion rates. It forces us to reconsider the very nature of cosmic time and the evolution of the universe itself. When we peer deep into space with our most powerful telescopes, we're essentially looking back through cosmic history. The most distant galaxies we can observe appear as they were when the universe was only a few 100 million years old, still in its cosmic infancy. These ancient galaxies are our primary window into understanding how cosmic structure formed and evolved over billions of years. But if we're embedded within a large underdense region, our view of cosmic history is necessarily filtered through this unusual environment. The light from those ancient galaxies has spent its entire journey traveling through space that may have very different properties from the cosmic average. This raises profound questions about how representative our observations of cosmic evolution actually are. The galaxies we see forming in the early universe, the rates of star formation we measure, and the chemical evolution of cosmic matter we infer from distant observations, all may be systematically biased by our location within a cosmic anomaly. The challenge becomes even more complex when we consider that cosmic voids themselves evolve over time. The KBC void we inhabit today may have had very different properties billions of years ago, when the light from distant galaxies first began its journey toward Earth. The underdense region may have been smaller, denser, or structured differently in the past. Understanding this temporal evolution of cosmic voids requires sophisticated computer simulations that can model the complex interplay between ordinary matter, and dark energy over cosmic timescales. These simulations suggest that voids do indeed grow and evolve significantly over billions of years, becoming larger and emptier as matter continues to flow toward denser regions. This evolutionary perspective adds yet another layer of complexity to interpreting our cosmic observations. Not only must we account for our current unusual location, but we must also consider how this location has changed over the cosmic time periods relevant to the observations we're trying to understand. The implications extend to some of the most fundamental questions in cosmology, including the nature of dark energy itself. Current observations suggest that dark energy makes up approximately 68% of the universe's total energy content and is responsible for driving the accelerated expansion of space. But these estimates are based on measurements that may be systematically affected by our location within a cosmic void. If the void hypothesis is correct, our local measurements of cosmic acceleration may not be representative of the universe as a whole. The apparent acceleration we observe could be partially due to the local effects of matter flowing out of our underdense region, rather than purely the result of dark energy acting uniformly throughout space. This possibility has led some researchers to propose that dark energy might not be a fundamental property of empty space, but rather an apparent effect that emerges from our unusual observational perspective. In this view, the universe as a whole might not be accelerating at all, and what we interpret as dark energy could actually be a consequence of large-scale inhomogeneities in the cosmic matter distribution. Such a radical reinterpretation of dark energy would have profound consequences for our understanding of fundamental physics. Dark energy has been one of the most mysterious components of the universe, requiring either exotic new forms of matter and energy or modifications to our understanding of gravity and space-time itself. If dark energy turns out to be an observational artifact rather than a fundamental aspect of cosmic evolution, it would eliminate one of the greatest mysteries in modern physics, while simultaneously creating new puzzles about the true nature of cosmic expansion and structure formation. The scientific community remains deeply divided on these radical possibilities. The observational evidence for cosmic acceleration extends beyond just local measurements, to include observations of distant supernovae in the cosmic microwave background. These diverse lines of evidence seem to confirm that cosmic expansion really is accelerating on a global scale. However, the void hypothesis adds important caveats to this interpretation. Even observations of distant supernovae could be systematically affected. If those supernovae are preferentially located in cosmic environments that are different from our own, the cosmic microwave background observations, while less susceptible to local effects, still must be interpreted through theoretical models that assume homogeneous cosmic evolution. As we continue to unravel these cosmic mysteries, one thing becomes increasingly clear: the universe is far stranger, more complex, and more varied than we ever imagined. What appeared to be a simple story of uniform cosmic expansion driven by dark energy may actually be a much more intricate tale of cosmic structure formation, local environmental effects, and observational selection biases that we're only beginning to understand. The void hypothesis represents just one thread in this increasingly complex tapestry of cosmic discovery. Whether it ultimately proves correct or not, it has already served a crucial function by forcing astronomers to question fundamental assumptions and explore alternative explanations for some of the most puzzling observations as we stand at this crossroads in our understanding of the cosmos. The next decade promises to bring unprecedented revelations about our cosmic environment and our place within it. Advanced observational programs, sophisticated theoretical models, and innovative analysis techniques are all converging to provide new insights into these fundamental questions about the nature of space, time, and cosmic evolution. The echoes from the Big Bang that first alerted us to this cosmic mystery continue to reverberate through space, carrying with them the secrets of our cosmic origins and our ultimate cosmic destiny. In learning to listen more carefully to these ancient whispers, we may finally begin to understand not just where we are in the universe, but why we find ourselves in such an extraordinary cosmic environment. The story of the cosmic void is far from over. Indeed, it may be just beginning to reveal its most profound secrets about the nature of reality itself. The journey to understand our cosmic address has taken scientists down increasingly exotic pathways, leading to discoveries that challenge not just our understanding of space, but our comprehension of existence itself. As we dig deeper into the implications of inhabiting this vast cosmic wilderness, we encounter phenomena that stretch the boundaries of human imagination and force us to reconsider everything we thought we knew about reality. Consider for a moment what it means to live within a structure so enormous that light takes 2 billion years to traverse its breadth. The human mind struggles to comprehend such scales. If you could shrink the observable universe down to the size of Earth, the KBC void would still be roughly the size of North America. We're not talking about a small irregularity in cosmic structure, we're talking about a fundamental feature of reality itself. But here's where the story becomes even more extraordinary. Recent investigations have revealed that the effects of living within this cosmic bubble extend far beyond simple measurements of cosmic expansion. The void appears to influence the very fabric of space-time in ways that were previously unimaginable. When Einstein developed his theory of general relativity, he showed us that massive objects curve space-time, creating the phenomenon we experience as gravity. But what happens to space-time in regions where matter is unusually sparse? The mathematics suggest something remarkable. Underdense regions like cosmic voids don't just contain less matter, they actually create subtle but measurable distortions in the geometry of space and time itself. These geometric distortions propagate outward from the void like ripples on a cosmic pond, influencing everything from the paths that light rays follow to the rates at which atomic clocks tick. The implications are staggering. Every measurement we make, every observation we record, every fundamental constant we determine, could be subtly influenced by these space-time distortions created by our unusual cosmic environment. This realization has led some researchers to propose that what we interpret as the acceleration of cosmic expansion might not be driven by mysterious dark energy at all. Instead, it could be a geometric effect arising from the complex space-time curvature created by large-scale cosmic inhomogeneities. In this view, the universe isn't actually accelerating uniformly. Rather, different regions experience different expansion rates depending on their local matter density and geometric properties. The mathematical framework for understanding these effects draws on some of the most advanced concepts in theoretical physics. Researchers are developing sophisticated models that incorporate not just the distribution of matter and energy, but the dynamic evolution of space-time geometry itself. These models suggest that cosmic voids like the one we inhabit create complex gravitational fields that can mimic the effects of dark energy over vast distances. But the mystery deepens when we consider the temporal aspects of our cosmic situation. The void we inhabit today is not the same structure that existed billions of years ago when the universe was young. Cosmic voids grow and evolve over time, becoming larger and emptier as matter continues to drain toward denser regions under the influence of gravity. This evolutionary process means that the cosmic environment we observe today may be fundamentally different from the one that existed when the most distant galaxies we can see were forming their first stars. The light from those ancient galaxies has been traveling through a cosmic void that has been continuously changing throughout their billion-year journey to reach our telescopes. Imagine trying to understand a movie by watching only the final scene, knowing that the theatre itself has been constantly renovating throughout the entire film. That's essentially the challenge facing astronomers as they attempt to interpret observations of the distant universe filtered through our evolving cosmic environment. The implications become even more profound when we consider quantum mechanical effects on cosmic scales. Modern physics suggests that empty space is never truly empty. Even in perfect vacuum, quantum fields fluctuate constantly, creating virtual particles that pop in and out of existence on timescales so brief they seem to violate the laws of energy conservation. But these quantum fluctuations don't occur uniformly throughout space. They're influenced by the local curvature of space-time and the distribution of matter and energy in their vicinity. Within a cosmic void, where space-time geometry differs from the cosmic average, quantum field behavior might be subtly altered in ways that could have measurable consequences for cosmic evolution. Some theoretical physicists have suggested that these quantum effects within cosmic voids could contribute to what we observe as dark energy. The reduced matter density in underdense regions might allow quantum fluctuations to behave differently, creating an apparent acceleration of cosmic expansion that emerges from the quantum properties of empty space itself. This quantum perspective on cosmic voids opens up entirely new avenues for understanding the relationship between microscopic physics and cosmic scale phenomena. The same quantum field theories that describe the behavior of subatomic particles might also hold the key to understanding why we observe accelerated cosmic expansion and why our local cosmic environment appears so unusual. The search for evidence of these exotic quantum effects has led researchers to examine the cosmic microwave background radiation with unprecedented precision. This ancient light, which has been traveling through space for nearly 14 billion years, carries subtle imprints of every cosmic structure it has encountered on its journey to Earth. Within the cosmic microwave background, scientists have identified patterns that might represent the signatures of quantum field fluctuations within cosmic voids. These patterns appear as tiny temperature variations that correlate with the large-scale structure of the universe in ways that suggest quantum mechanical origins. If confirmed, these quantum signatures would provide the first direct evidence that microscopic quantum processes can have measurable effects on cosmic scales. Such a discovery would revolutionize our understanding of the relationship between quantum mechanics and general relativity, potentially pointing the way toward a unified theory of quantum gravity. The implications extend beyond pure physics to touch on some of the deepest philosophical questions about the nature of reality itself. If our observations of the cosmos are fundamentally shaped by quantum processes occurring within our local cosmic environment, what does this tell us about the objectivity of scientific knowledge? This question becomes even more intriguing when we consider the possibility that cosmic voids might be more common than previously thought. Recent surveys of the distant universe have identified numerous other large-scale underdensities that rival or even exceed the KBC void in size and emptiness. If such structures are natural and inevitable consequences of cosmic evolution, then most observers in the universe might find themselves in similarly unusual environments. This statistical argument suggests that what we consider typical cosmic conditions might actually be quite rare. The dense, highly structured regions of the universe that contain most galaxies and stars might be cosmic metropolises where conditions are too chaotic and violent for the emergence of complex structures like planetary systems and biological life. From this perspective, cosmic voids represent not cosmic wastelands but cosmic sanctuaries where matter can organize itself into the delicate configurations necessary for complexity and consciousness to emerge. The very fact that we exist to observe the universe might be intimately connected to our residence within this vast underdense region. This anthropic interpretation of cosmic voids has profound implications for our search for extraterrestrial intelligence. Rather than focusing on the galaxy-rich regions of the universe, where most stars and planets reside, Perhaps we should be looking for signals from other cosmic void dwellers, who, like ourselves, might have emerged from the quiet, stable environments that these underdense regions provide. The technological challenges of detecting such signals would be immense. Cosmic voids are, by definition, sparsely populated with matter and energy sources. Any civilization that emerged within such an environment would be separated from its nearest neighbors by distances so vast that even light-speed communication would take millions or billions of years. Yet these same vast distances might also provide advantages for advanced civilizations. The low background radiation levels within cosmic voids would make sensitive astronomical observations easier to conduct. The reduced gravitational interference from nearby massive objects would facilitate the construction of delicate scientific instruments and space-based observatories. Perhaps most intriguingly, the unusual space-time geometry within cosmic voids might offer unique opportunities for exotic physics experiments that would be impossible in denser cosmic environments. Advanced civilizations might find ways to exploit the geometric properties of underdense regions to achieve feats that seem impossible according to our current understanding of physics. These speculative possibilities highlight how much we still don't understand about the fundamental nature of cosmic voids and their role in cosmic evolution. As our observational capabilities continue to advance, we're beginning to probe these mysterious regions with unprecedented detail and precision. The James Webb Space Telescope has already begun to reveal surprising details about galaxy formation within cosmic voids. These observations suggest that star formation and galaxy evolution proceed very differently in underdense regions compared to typical cosmic environments. Galaxies within voids appear to form more slowly and retain more of their primordial gas content, creating stellar populations with unusual chemical compositions. These findings have important implications for our understanding of cosmic chemical evolution. The heavy elements necessary for planet formation and biological chemistry are produced within stellar cores and dispersed into space when massive stars explode as supernovae. If star formation rates are systematically different within cosmic voids, the abundance and distribution of these crucial elements might also be affected. Such chemical differences could have profound consequences for the emergence of life within void environments. Lower metallicity might reduce the probability of terrestrial planet formation, while also potentially creating more stable stellar environments, where habitable zones remain unchanged for billions of years. The interplay between these competing factors creates a complex landscape of possibilities for astrobiology within cosmic voids. While some conditions might be less favorable for life as we know it, other factors could create unique opportunities for alternative forms of biological organization that we haven't yet imagined. Recent advances in computational modeling are beginning to provide insights into these complex evolutionary processes. Sophisticated simulations can now track the formation and evolution of cosmic voids over billions of years, revealing how these structures influence everything from galaxy formation to the distribution of heavy elements throughout space. These simulations suggest that cosmic voids undergo dramatic transformations over cosmic time. Through the cosmic lens, we've journeyed deep into the silent expanses of the universe, into the vast and mysterious cosmic voids that stretch between the great filaments of galaxies. These regions, once thought to be nothing more than empty space, are revealing themselves to be dynamic laboratories, where quantum physics and cosmic evolution intertwine. What was once seen as absence may in fact hold the deepest clues about how reality itself is structured. The more we study these underdense realms, the more we realize they are not voids of nothingness but canvases painted by the faintest quantum fluctuations, ripples that may have shaped galaxies, stars, and even life. Every temperature variation in the cosmic microwave background, every whisper of expansion, carries the fingerprint of forces that connect the smallest particles to the largest cosmic structures. It's a reminder that the universe is a single, seamless fabric, woven together by invisible threads of quantum energy and space-time curvature. From a philosophical perspective, the discovery that we might live inside one of these immense voids reshapes our sense of cosmic identity. Perhaps our position in this vast emptiness is not accidental. Perhaps it's the quiet stability of our underdense region that allowed complexity and consciousness to emerge. The silence of the void might have been the cradle for awareness itself, allowing the universe to look back upon its own creation through the eyes of intelligent life. And if that's true, then cosmic voids are not just distant curiosities. They're essential to understanding why we exist at all. The calm between the chaos, the silence between the galaxies, these may be the spaces where creation takes its deepest breath. They might even be the cosmic sanctuaries where other civilizations scattered across the great darkness are watching us through their own lenses, wondering the same questions we ask today. This is the vision of Cosmic Lens, to explore not just the visible wonders of the universe, but the hidden truths that lie in its emptiness. Because sometimes to understand the universe, we must not only look at what shines, but also at what doesn't. Subscribe, stay curious, and keep your eyes open for the cosmos. Still has secrets to share with those who dare to look deeper. Now, modern cosmologists must grapple with the possibility that our cosmic reference frame itself is highly atypical. The void hypothesis also raises intriguing questions about the anthropic principle and the apparent fine-tuning of physical constants that allow complex structures like galaxies, stars, and planets to form. If cosmic conditions vary significantly between different regions of the universe, perhaps the apparent fine-tuning we observe is simply a selection effect. We find ourselves in a region where conditions happen to be suitable for the emergence of observers like ourselves. Yet, even as we contemplate these profound implications, the scientific process continues to unfold with characteristic rigor and skepticism. Independent research groups around the world are working to verify, challenge, and extend the void hypothesis using different datasets and methodologies. Some studies have found evidence supporting the existence of large-scale underdensities in our cosmic neighborhood, while others have questioned whether such enormous voids are consistent with our current understanding of cosmic structure formation. The scientific community remains divided on the interpretation of the evidence, as is appropriate for such a potentially revolutionary discovery. The debate continues to evolve as new observations become available and theoretical models become more sophisticated. Computer simulations of cosmic structure formation are being refined to better understand how large voids form and evolve over cosmic time. Observational programs are being designed to test specific predictions of the void hypothesis against alternative explanations for the Hubble tension and other cosmological puzzles. What makes this scientific detective story even more compelling is the elegant way that seemingly unrelated cosmic mysteries begin to connect once we accept the possibility that we're living in this vast underdense region. The void hypothesis doesn't just address the Hubble tension, it potentially explains a constellation of puzzling observations that have been accumulating in the astronomical literature for decades. Consider, for instance, the peculiar behavior of our own galaxy's motion through space. The Milky Way is racing through the cosmic web at approximately 602 nm relative to the cosmic microwave background. This might sound fast, but it's actually surprisingly slow compared to what we observe for other galaxies in similar cosmic environments. Most galaxies show much higher, peculiar velocities as they're pulled around by the gravitational influence of nearby massive structures. Our galaxy's relatively sedate motion through space has long puzzled astronomers, but if we're located near the center of an enormous cosmic void, this leisurely pace makes perfect sense. There simply isn't enough nearby matter to gravitationally accelerate our galaxy to the extreme velocities we see elsewhere in the universe. We're coasting through a cosmic desert, where the gravitational landscape is remarkably flat and gentle. This realization connects to another long-standing puzzle in cosmology known as the local group timing problem. Our galaxy and the nearby Andromeda galaxy are currently approaching each other and will likely collide in about 4 billion years. But when astronomers try to model the orbital dynamics of this local galaxy pair, they find that the timing doesn't quite work out according to standard cosmological models. The problem is that there doesn't appear to be enough matter in our immediate cosmic neighborhood to account for the gravitational binding of the local group. Either there's missing dark matter that we haven't detected, or the dynamics of galaxy interactions work differently than we think. But if we're embedded within a large underdense region, the reduced matter density naturally explains why local gravitational dynamics appear anomalous compared to theoretical predictions. The void hypothesis also sheds new light on observations of the cosmic web itself. When astronomers map the large-scale structure of the universe, they see a complex network of filaments and nodes, where galaxies cluster together, separated by vast empty regions. But our local cosmic neighborhood appears to be remarkably smooth and featureless compared to these distant cosmic metropolises. This smoothness extends to the cosmic microwave background radiation itself. When we look at the temperature fluctuations in this ancient light, we find that our local sky is unusually uniform. There are fewer hot and cold spots than we would expect based on the cosmic average. This phenomenon, known as the cosmic microwave background cold spot, has been another persistent puzzle in cosmology. If we're viewing the cosmic microwave background from within a large void, this apparent smoothness becomes much easier to understand. The reduced matter density along our line of sight to the last scattering surface would naturally create the appearance of a colder, more uniform region in the ancient cosmic glow. What appeared to be an anomaly in the cosmic microwave background might actually be a natural consequence of our unusual cosmic address. The implications ripple outward to affect our understanding of cosmic structure formation itself. The current theoretical framework suggests that the universe began in an almost perfectly smooth state, with tiny quantum fluctuations serving as the seeds for all subsequent structure formation. Over billions of years, these microscopic variations grew under the influence of gravity to become the galaxies, clusters, and superclusters we observe today. But this story of gradual structure formation has always struggled to explain the existence of extremely large-scale structures like the KBC void. According to standard models, it should be nearly impossible for such under dense regions to form within the age of the universe. The gravitational forces simply haven't had enough time to evacuate matter from such vast volumes of space. This is where alternative theories of cosmic evolution begin to look more attractive. Some cosmologists have proposed that the early universe experienced multiple phases of rapid expansion, not just the single inflationary epoch that's part of the standard model. These extended inflation scenarios could naturally produce larger-scale structures than conventional models predict. Other researchers have suggested that the dark energy driving the current acceleration of cosmic expansion might not be constant over time. If dark energy has evolved or fluctuated throughout cosmic history, it could have influenced structure formation in ways that standard models don't account for. Regions that experienced slightly different dark energy densities in the past might have evolved into the supervoids and superclusters we observe today. The most radical possibility is that our understanding of gravity itself needs revision on cosmic scales. Modified gravity theories, like MONDI, naturally predict enhanced structure formation compared to dark matter models. In these frameworks, the apparent effects we attribute to dark matter actually arise from our incomplete understanding of how gravity behaves when accelerations become extremely small. These theories make specific, testable predictions about how matter should behave within and around cosmic voids. Unlike dark matter models, which require the existence of exotic particles that have never been directly detected, modified gravity theories propose changes to the fundamental laws of physics that govern all matter and energy. The observational tests of these competing ideas are becoming increasingly sophisticated. Astronomers are now able to measure the three-dimensional positions and velocities of millions of galaxies, creating detailed maps of how matter flows through the cosmic web. These observations reveal complex patterns of streaming motions that extend across hundreds of millions of light-years. Recent analyses of galaxy velocity data have revealed bulk flows that exceed what standard cosmological models predict. Entire regions of the universe appear to be streaming in coherent directions at speeds of several hundred kilometers per second. These large-scale motions could be the signature of matter flowing out of enormous voids like the one we may inhabit. The velocity patterns also provide crucial tests of different theories of gravity and dark matter. Each theoretical framework makes distinct predictions about how galaxies should move in response to the underlying matter distribution. By comparing these predictions with increasingly precise observations, astronomers can begin to distinguish between competing explanations for cosmic structure formation. But perhaps the most profound implication of the void hypothesis concerns the fundamental question of cosmic representativeness. If our observations are systematically biased by our location within a cosmic anomaly, how can we ever hope to understand the universe as a whole? This challenge goes to the heart of the scientific method itself. Throughout the history of astronomy, we've repeatedly discovered that Earth occupies no special place in the cosmic order. We're not at the center of the solar system, our sun is not at the center of the galaxy, and our galaxy is not at the center of the universe. This principle of cosmic mediocrity has been a guiding assumption in cosmology for over a century, but the void hypothesis suggests that, while we may not be at the center of anything in particular, we may indeed occupy a highly unusual cosmic environment. This doesn't violate the principle of cosmic mediocrity in any absolute sense. After all, if supervoids like the KBC void are natural consequences of cosmic structure formation, then some observers must necessarily find themselves in such environments. The question becomes whether observers like ourselves are more likely to emerge in typical cosmic environments or in unusual ones. Dense regions of the universe experience more frequent galaxy mergers, higher rates of star formation, and more intense radiation environments, all of which could be harmful to the development of complex life. Conversely, the quiet, stable environment within a cosmic void might actually be more conducive to the emergence of intelligent observers. Planetary systems can evolve undisturbed by cosmic catastrophes for billions of years. The lower background radiation levels reduce the risk of mass extinctions caused by cosmic ray bombardment or gamma-ray bursts from distant stellar explosions. This anthropic perspective on cosmic voids opens up fascinating new avenues for thinking about the distribution of life in the universe. Rather than focusing our search for extraterrestrial intelligence on the dense cosmic cities where most stars and planets reside, perhaps we should be looking in the cosmic suburbs and wilderness areas where conditions might be more favorable for long-term biological evolution. The void hypothesis also has profound implications for our estimates of how common life might be in the universe overall. If most potentially habitable worlds exist in dense cosmic environments where catastrophic events are more frequent, the actual probability of complex life developing might be much lower than optimistic estimates suggest. On the other hand, if cosmic voids provide safe havens where life can develop and thrive over cosmic timescales, there might be entire populations of civilizations scattered throughout these underdense regions too far from the galactic mainstream to be easily detected by conventional search strategies. These speculations remain highly theoretical, but they illustrate how the void hypothesis forces us to reconsider fundamental assumptions about our place in the cosmic order. The universe may be far more varied and complex than we've imagined, with different regions offering vastly different environments for the development of stars, planets, and life itself. As observational technology continues to advance, we're gaining unprecedented ability to test these ideas against reality. The next generation of extremely large telescopes will be able to detect and study individual galaxies at distances that will allow us to map cosmic structure well beyond the boundaries of any local void. Space-based observatories, like the proposed Nancy Grace Roman Space Telescope, will survey billions of galaxies across cosmic history, providing the statistical power needed to definitively characterize our cosmic environment. These observations will reveal whether the patterns we see in our local cosmic neighborhood are truly anomalous or represent normal variations in cosmic structure. Perhaps most excitingly, advances in gravitational wave astronomy are opening entirely new windows into cosmic structure. As detectors become more sensitive, they'll be able to observe gravitational waves from increasingly distant and ancient cosmic events. These observations will provide completely independent probes of the matter distribution between us and the most distant reaches of the observable universe. The accumulating evidence from multiple observational approaches is painting an increasingly detailed picture of our cosmic environment. Each new measurement adds another piece to a puzzle that may fundamentally reshape our understanding of the universe and our place within it.